Hello everyone, and today I'm going to show you how to solve house robber using dynamic programming. A lot of videos just go directly to the bottom-up dynamic programming. In this video, I'm going to show how do you think of the recursive solution and then lead up to the top-down. So here is what this problem is talking about. So we are planning to rob a series of houses where each house has a certain amount of money. However, we do run into the constraint where if we rob two adjacent houses, we will get caught. So basically, our objective is to rob so that we can obtain as much money without being caught by the police. So this is kind of like an optimization problem. And I think with arrays, you can use indices as well. So that is potentially grounds for a dynamic programming problem. So let's go ahead and trace some of the examples. So then here we have nums equals 1, 2, 3, 1, where each of these elements represent how much money each of these houses have. So then the output is going to be 4. In fact, 4 is the optimal solution. You can rob house 1 and 3. But notice here, you cannot rob house 2 and 3 since 3 is adjacent to this one and 2 is adjacent. Now these examples obviously are not the best, I have to say, because it doesn't account for some of the edge cases that you may encounter in this problem. Example 2, we have our nums equals 2, 7, 9, 3, and 1. We have our output is 12. So we can rob the first, third, and fifth house. So that's the example code. Now let's go into some edge cases here. Is that you may come to the assumption, right, that the optimal solutions are, are alternating. You can rob alternating houses. But this example is wrong because you can rob the first and fourth house and still get the maximum. So this is the non-alternating edge case. The second case is that if you have some sort of greedy algorithm. So what does greedy mean in this context? Since this is a maximization problem, usually every decision you'll be taking the maximum cost. But we are dealing with constraints, so we can't just pick 9 and then we can't pick 8. But even if we then pick 9 with these constraints here, this is still not going to be the best. As you see, if we rob 8 and 6, is going to be much better. So in some cases, right, you can pretty much guarantee that the first element is not always going to be the house to rob. So that's pretty much trivial. So let's go ahead into some example code. Let's see if we can write down a sort of decision tree and how we can go ahead and break this down. So instead of having, now many people are thinking, instead of having to like go back and update all of these, you can just think about yourselves robbing these houses sequentially. So for example, if you're robbing house 2, then basically you're almost guaranteed that you probably don't care if you have robbed this first house or not. But yeah, essentially we have some sort of model that'll allow us to go forward. We only go forwards here unless we branch back to a decision. So we're only going to go back. So pretty much if you saw the subsets video, this brute force solution has kind of the same intuition, except we're now going to be working with adding up amounts. So here we have 4, 1, 2, 8, 9, 6. Let's trace through the input, and I have highlighted the optimal solution. We have 4, 8, and 6. 18 is going to be the best right here, and I'm going to show you why. So think about yourself as a robber. So you're starting from the beginning, right? And then we're going to be considering, but then, since dynamic programming is recursive, we're going to have this brute force approach. So we're always going to be treating this like the beginning. So we have this sort of complexity removed. So basically, we have, so at 2 decisions here. Let's say here we have at 4. We can choose to take, or we can choose not to take. There is a method called dynamic programming that allows to do this. So ultimately, it takes, if you have this brute force, so BF, you can go into top down, so memoization. Never mind. And then pretty much what we want to do is we want to start and take everyone. Now, it doesn't make sense initially, but what we want to do is how many binary numbers can be represented using 6 digits. So basically what this easy hack you can say is think about, assume there's another digit. So when will this be 1? What will be the first number which will turn 1? So this will be 2 to the 0, 2 to the 1, 2 squared, 2 cubed, and then 2 to the 4, 2 to the 5, 2 to the 6th. So basically here, you have 2 to the n plus 1. So 2 to the n plus 1, so if this right here is 0, 1, 2, 3, 4, 5, then basically here, this is going to be 6. There's going to be 64 combinations, which is going to be very tedious to draw out. So this is why I'm going to be drawing out a few decisions here. So we can choose to take, or we can choose not to take it. If we choose to take the money, then we will be accumulating an amount. So we will add 4 to our current stash. However, we will move to the next house. But if we choose to rob, then we cannot rob the adjacent house as well. So that's why we have 2, 8, 9, and 6. Otherwise, we're going to have something like 1, 2, 8, 9, and 6. So let's say here we have this subproblem. We're not going to take amount into our subproblem. We're not going to pass it into our parameter. Our focus is splitting the array. And now essentially what we want to do, and this may twist your mind, is we want to keep splitting the array. And you'll see why. Because we split the array. Why not do it again? Hold on, so I think it'll be much cleaner. We will just be accumulating this cost, and pretty much this is just going to be covered in this sort of subproblem as well. So what we're going to have is we're going to rob or skip, and then what we want to do is instead of just taking this 4, we're going to take this 2, and then we're going to have this 9 and 6. And then we have 0 plus, we skip this index. So 8, 9, and 6 is going to be the next thing. For 9 and 6, we're going to have another choice. We can choose to rob or skip. Oh yeah, also, we can't rob this. So this is why it's going to be this. So 9 plus something right here. So this is actually going to be 0. Right now, we're only going to be considering what is actually in the brackets here. So in here, we have 0. And then we can split up right here. Or if we don't choose to take it, then we're going to be stuck with this branch. Regardless, we are going to be stuck with this. So 6 plus this empty array. So the empty array is a base case. So this is going to be 0. And this is going to be 0. And notice here that whenever we reach something in an empty array, we're going to have 0 as an array. So we're going to have 0 as default value. So once we reach our base case, once our index is no longer in bounds, which of course we can start checking here. We're not obviously going to be making a new array. We're just going to keep a starting index here. But yeah, we're not going to be packing this. We have to do some sort of letters in order to symbolize this. So yeah, after the base case right here, we have we can add continuously, so that's going to be 6 plus this, and then 0, and then plus this. And now how would we know what these particular subproblems are? So since we want to maximize cost right here, so if we have this house, why not rob it? So this is going to be the maximum. So this is going to be the maximum of this. So we got 6, and then we have 0. So that's going to be 6. This is going to be 9. And then we have the maximum of 6 and 9. But we also have to add, so particularly for this subproblem, we have 11. But 11 plus 2 is going to be 13. And then here, if we decide to, skip, pretty much vice versa, and then we should pretty much should go down to transform all of our base cases here. Now, a common mistake that I've been attempting to do is try to memoize while keeping track of the amount. You don't need to do that. It's kind of overkill. Given that we want to do the brute force, we need public int, and then we could also call this rob. So we're going to take in the same array because we also want to be able to access the array elements in the helper. So speak about our recurrence relation. It's going to be the maximum of these two decisions here. So let's go ahead and take public int rob, and then basically here we're going to have some sort of index. And basically what we want to do is if we rob, then pretty much the index increases by 2. So the best case would not be to do if index equals nums.length, but preferably if index is greater than or equal to nums.length. And this is so that we can account for decisions that involve robbing the last house. So what we want to do is return 0. We don't want to simply return anything here. What we otherwise want to do is, for this particular method, we want to follow this schema. We want to go ahead and take the maximum of all these decision points. So return the maximum, so math.max of, if we decide to take it, will be modeled, so this function call will be modeled like rob, and then we have nums, and then we have our index plus 2, but then we also have to add the current amounts. So plus, we're going to have nums, and then we have our index, so index here. And then we also want to skip this, so we have rob, and then we have nums, and then we have index plus 1, and then nothing else. So let's go ahead and actually call this. So we have rob, and then we have our nums, and we're trying to start from the initial problem. So we have 0 here, and let's see if this is right. And it looks like that's great. Let's go ahead and try to submit it. As you see, it's taking a while, and we get a time limit exceeded. Now, 55 out of 70 test cases passed. Now, why could this be? That is pretty much going to be where dynamic programming shines. So we're going to talk about top-down dynamic programming, also known as memoization. So in top-down dynamic programming, you're going to have some sort of memo or cache where you're going to store solutions to those subproblems that you compute. So for example, once you reach a base case, right, you can pretty much set the cache elements to, let's say, something 0. You don't really need it though, since 0 is kind of a trivial number. So yeah, right now we're just going to have a cache of size 6. So we have right here, and this will refer to the subproblem at that particular index. So 0, 1, 2, 3, 4, and 5. And a subproblem at a particular index is basically going to refer to whether you start at index 0, or whatever the problem starts at index 1, problem starts at index 2, and pretty much etc. But yeah, if we have something empty, it's going to be 0, and pretty much adding 0 doesn't do anything, so we're not going to include another element specifically for that. But yeah, this is going to refer to this problem. So our objective is to actually return this particular value. So this is the value that you must return. So let's say here, you have this. This is probably the first subproblem that we're going to reach a base case on. So we have 6, and then we're going to have the maximum of if we rob this or not. Then we have our base case, which is 6 plus 0, and then we have 0. So this is going to be 6 and 0. So 6 is actually going to be stored inside the cache. So ultimately in this sort of decision, if we rob here, then we will be doomed to reach the same thing again. So why not just call the value from the cache? So that is the intuition of what this solution is going to be. So this is what's going to be something like this. Now, how will we know what value our cache is typically supposed to be? So this is a maximization problem. So our default value should be -1. So once we're at some sort of recursive call, then we should investigate whether the current cache cell is -1 or something else. If it's not -1, then the subproblem has already been computed, and we can return it from the cache. Otherwise, we will have to follow this sort of recurrence relation here. So here, I am using the same recursive solution, but I am actually going to have another parameter called cache. So it's cache, or even better, dp, as it's going to be much better as it is. So let's call this thing dp, and that's going to be the same size as our nums array. So new int, we have nums.length. And then what we want to do is that we want to set all these elements to -1. So you can use arrays.fill. The fill method essentially fills all the elements in an array to a certain value. So for example, if you pass in this dp array of size 6, and if you pass -1 here, all 6 elements will be -1. So basically, that is going to be what this is. And then what we want to do is to return rob, and then we have nums. We also have to pass dp here. But speak about this. We also have to modify this dp and make use of it. Right now, it's just a recursive solution. But you want to investigate this. So if index is greater than or equal to nums.length, this is still going to be the same because we're not going to have a cache element for this. We are just going to say equals to -1. Then basically, if we haven't computed the subproblem, then we want to go ahead and set the current index to the result of what we have our max decision. So math.max, we have this thing here. We also have to modify the parameters so that we can take in this dp as well. So dp and dp. Otherwise, what we want to do is return the cache at that particular element. Hold up, dp. I meant to say dp at index. I'm so used to like doing cache, I don't know why. But yeah, pretty much that should be it. So, but otherwise, this is going to be the maximum of all these results. Let's go ahead and run this problem. And we should be able to get this result. Let's submit. And there we go. Now, why did this memoized solution provide much better time than our recursive solution we're dealing with? Of course, we have 2 to the n combinations, we call that. So we have to make 2 to the n sort of decisions. And even if we reach something that we have already computed before from other tasks, we're still going to have to recalculate them in the brute force. So let's call this brute force. Our time of complexity is going to be O of 2 to the n. Consider our decision tree as well. We have 1 times however many nodes are in the next layer, So that's 1 times 2 times 4 times 8. Usually in Big O, remember that constants and lower order terms are drops, so remember that 3 times 2 to the n is the same as 2 to the n in this case. And I should say O of 3 to the 2 to the n equals O of this thing here. Now, if we have a memoization solution, instead of having to compute the subproblems here, we have this O of 1 lookup. So therefore, we have our memoization, let's call this M. Our memoization time complexity is actually going to be O of n. Now, why is the memoization time complexity O of n? Now, even though we arrive to the solutions of the subproblems, we aren't just breaking the problems down. We're going to save a lot of time, and we're only calculating results to one subproblem. Otherwise, you're pretty much having O of 1 access. Every time you reach 6 is going to be an O of 1 operation to the cache, except you're computing the first time, in which case you must make the 2 decisions. So that is pretty much going to be the time complexity here. Let's talk about the space complexity. So the space complexity basically refers to how much memory is being taken by running this program. So particularly since we're utilizing recursion, our algorithm is going to utilize some sort of depth first search. So pretty much all these calls are going to be put on a stack. And pretty much once we're done with them, all these calls will be popped from the stack. So notice that not all of these calls are going to be on the stack at the same time, which is why the space complexity is not 2 to the n, rather the height of the decision tree. So this is going to be O of n. And then even if we memoize this, we have another cache right here. So this is going to be O of 2n. Which, by the way, constants are dropped in Big O, so the space complexity is O of n. There is a 2-pointer dynamic programming solution that provides much better space complexity. However, this time, we're just dealing with memoization. So yeah, that's pretty much going to be it for this problem. If you guys enjoyed, make sure you leave a like, subscribe, and of course, see you guys in another video. Peace out.